Okay, I also want to now do a couple examples working with infinite sets out of the chapter review. This is on page 97. I want to look at problem 55, which says to show that the set is infinite by placing the set in a one-to-one correspondence with a proper subset of itself. So in problem 55, we have the set 2, 4, 6, 8, 10, etc. Basically, we have the even numbers is the set we're working with here. So our job is to put this in one-to-one correspondence with a proper subset. Now, the easiest way to create a proper subset of any set is to just remove the first term. Because to be a proper subset, all the elements must be in the previous set, but they can't be the exact same number of elements. So if I get rid of element 2 and just start with 4, I will have created a proper subset of our original set. And so our correspondence will be that 2 maps to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. And then the part of it here that I've not yet addressed is what are the general terms. And this is the trickiest part of these sets. It's determining what expression in terms of n needs to go here to represent the general term. So if we think of this as the 2 is the first element, the 4 is the second, the 6 is the third, the 8 is the fourth, and the 10 is the fifth term, how do I get the nth term? So I'm looking at what is the relationship between the 2 with the 1, the 4 with the 2, etc. over here to what expression with n. What do I have to do to the 1, 2, 3, 4, 5 in order to get 2, 4, 6, 8, 10? The answer is I have to multiply by 2, right? 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 5 is 10. So the nth term needs to be 2n. So for instance, if you wanted to know what the 80th term was in this set, the 80th term would be 2 times 80, 160. So the last thing I now need to do to complete the one-to-one correspondence is to figure out what the nth term is of the proper subset. So you basically look at the relationship here between these numbers and the numbers they're mapped to. What you should notice is that each of these numbers is exactly 2 greater than the number up here. So the number that goes here, or the expression that goes here, needs to be exactly 2 greater than 2n plus 2. And now we've demonstrated that this set is an infinite set because we've placed it in one-to-one correspondence with a proper subset of itself. So let's also look at one of these next types of problems, problem 57, which asks us to show that the set has cardinal number a left null by setting up a one-to-one correspondence between the set of counting numbers and the given set. So the set we're given is 5, 8, 11, 14, 17, ... And I'm going to put it in one-to-one correspondence with 1, 2, 3, 4, 5, ... n ... because these are the counting or natural numbers. This is slightly easier, I think, than problem 55 because you only have to figure out one general term. The natural numbers are always this set, and the idea is just to figure out what's the general term up here. So we need to look at the relationship of these numbers. If this is the first term, second, third, fourth, and fifth terms, what's the expression for the nth term is what we're trying to determine. What you should notice is that they each skip by 3. Now a common mistake here is to write n plus 3. But that's not going to work because 1 plus 3 is not 5, nor is 2 plus 3 or 3 plus 3 11, or 4 plus 3 14. It's not correct. The 3 that they're skipping by actually ends up being the coefficient of n. You need to multiply n by 3 and then either add or subtract something to it. So if I multiply 1 by 3, I get 3. If I want to get 5, I need to add 2 more. And you can see that pattern will hold if you take the second term. If you multiply 2 by 3, you get 6, and add 2 more, you'd be at 8. If you multiply 3 by 3, you get 9, add 2 more, and you get 11. So this expression will give you the nth term. So for instance, if you wanted to know the 50th term in this set, it's 3 times 50, 150 plus 2. So 152 would be the 50th term in that set. And so after you've shown this, if we were to name our first set, let's say it was set A, then we could come to the conclusion that the cardinal number of set A is A left null.